Do I have amplification? Oh, it sounds like I do. Well, you know, I'm going to start by talking about these pictures that you've been looking at and give you a bit of orientation, because I don't know if many of you can make any sense of them. This actually is the recording of some aurora that has happened at Toolik Lake, and it's been taken with something called an all-sky camera. An all-sky camera is a device that can see the whole sky at one time. And I'm just going around with my pointer showing where the edge of the sky is. This is where the horizon is in this picture, all the way around the edge here. And in the middle is what you see looking straight up. And to understand the orientation, you ought to think of yourself lying on your back with the feet towards the North Pole and looking up at the sky, and then the pieces that you see in here are in the right place. So this is the south then, up at the top here, and the north is down at the bottom. And the east is on the right, and the west is on the left. So you can get an idea of where things are in relation to the position where the camera is in operation. You can also see green aurora. Most of you are familiar with green aurora. It might have been a long time since you saw it. Let's see, is everybody in agreement that we haven't seen much aurora recently? I see some nodding heads. You know, I have good news for you. You see, just as the days are getting longer, the aurora is coming back. And so it doesn't go on annual cycles, of course, for the aurora. It goes on 11-year cycles, but we're going to see the aurora coming back because we're climbing out of solar minimum. But the purpose of this talk is to review with you what has happened at solar minimum and to understand why we have aurora, which actually is so frequently present at places like Toolik Lake. Toolik Lake, for some of you, is a familiar place, but if you go up the Haul Road towards Prudhoe Bay, you're only a few tens of miles off Prudhoe Bay when you're at Toolik Lake. So let me just say that the other things you can see here are lights on the roads around, or on the camp around Toolik Lake. And what you're seeing here are the lights of the Toolik Lake camp itself. So this is then something that you're going to find familiar in this talk, the all-sky camera view of things. I should also say, because I'm going to get onto this a little bit later, but I'll say it, the color that you see in the aurora has to do with what is in the atmosphere that is creating this light. This color green comes from oxygen. And for the most part, you can only really see green here. The lighter colors are overexposures in this particular presentation. So I'm going to stop this for now and go on to my regular presentation. So my topic is auroras at solar minimum. And I have got some co-authors here, some people who know much better than me. Shinichi Akasofu, he, until recently, was the director of the International Arctic Research Center, and before that, he had the position which I now occupy at the Geophysical Institute. And he is probably one of the most famous scientists in Alaska, one of the 1,000 most famous scientists on auroras. And there's Charles Deere, who, if you look at the forecast for auroras on the Geophysical Institute website, you'll see his name frequently. He's the chief forecaster. And Dirk Limmertsheim, who is also an auroral specialist, who is his deputy in doing forecasts. And Hans Nielsen, who is now emeritus professor at the Institute, and also associate director, with whom I've had many discussions on the aurora. And at the bottom here, I've got a bibliography listing for this. You'll find, if you go on the back table, that there's a bibliography handout. So this is libguides.library.uaf.edu/aurora. That gives you a number of books and other applications that you might want to find to help you on this topic. So here's the reason why we are at solar minimum. This is a graph of sunspot number. And the graph goes against time here. So it's this January of 2000 2000 going 2001 through 3, 4, 5, 6, 7, 8, 9, 10, and onwards, going up to 2019. And here's the sunspot number. Now there's a tricky thing about sunspot numbers. You'd think it would be easy. Sunspot numbers means the number of sunspots. It doesn't. It's a number derived from the number of sunspot numbers, but it isn't the actual number of sunspots. So if you actually want to know, if you saw 150 up here on the sunspot number, how many sunspots might you see on the sun? The answer is about 10. For some reason, the person that scaled these made them about 15 times too many. So this is then at maximum here. We're seeing about 10 sunspots on the sun at one glance. And then getting down to here at 2009, we're seeing none at all. This is a very, very long, deep minimum for sunspot minimum that we've gone through. Basically, there hasn't been much to see in the sky in Aurora since about halfway through 2005 and the present time. But as you can see, the sunspot number is coming up. This red curve here is the latest that I could find on a prediction as to what's going to happen to the sunspot number over the upcoming years. And so we'll expect to see another solar maximum somewhere around 2013. And by the time we get to the end of 2011, we should be well on our way to that maximum. So that's what I'm saying about the return of the auroras. It's going to happen probably by the end of this year. So then we have to ask the question now, are these cycles normal? Well, we're only seeing part of a cycle here, but this is the cycle of about 11 years is what is found over a long period of time. And so it's not at all unusual for us to find a solar minimum like this. But I also have to say that you don't find the solar minimum in the power of the warmth of the sun. You don't find nearly so much variation in the optical and infrared light that comes from the sun as you do in the ultraviolet, and also in the particles that create the aurora. And so this is a really big change in the behavior of the sun here in sunspot number, but it's less than 0.1% of the infrared radiation that is changing on this 11-year cycle. It's not enough for us to notice. And that's why you don't find it in the weather forecast. Okay, so here is, this is taken from the maps that are used in the Geophysical Institute Aurora forecast. And what it shows is for one particular day, it was actually, it's about like this today and yesterday. This is where you might see the aurora at midnight in Alaska under these current magnetically really quiet conditions. And this circle here is the location of the edge of that field of view that was in the picture that you've just been looking at. So you could see that you can't see as far as Fairbanks in the sky in looking at that aurora, or saying the other way around. The Fairbanks is not going to see much of an aurora, which is up here at Toolik Lake. So then if we remember what I said about this picture, that the top is south and the bottom is north. That's inverted from what we see, so I drew it upside down so that now it's the way it is in our all-sky cameras. And now you see, if we remember that, then when we see the bottom of the picture, it's north, and the top of the picture, it's... And here's now more of that recording, but this is a different day. This is now the 12th of February 2010, and this clock up here shows the passage of time in the real time at Toolik Lake. And you'll notice it's going pretty fast. It's actually going some 70 or 80 times normal. And you'll notice that it looks pretty jittery when it's actually, you can see something. It's not always showing aurora, but it will come back in a minute. This is really very, very slow motion when you're looking at it at real time. Looks very fast here, but it isn't fast at all. But you ought to see that most of it looks like it's in the north. It's at the bottom of the picture. And so if you remember the map that I was showing you just now, if I go back to it, oops, I really want to go back here. Most of this aurora is up here. So it's a long way away from Fairbanks. It's happening, but it's a long way away. So let's look at a bit more of it. And you'll see that it will start on occasions to get further and further south. And then you might see a little bit of a flurry of activity at that point, and then it will go back north again. Now, this is quite a normal cycle of events in the aurora, and it happens quite often, of course, during the year when we're near solar maximum. It will happen over Fairbanks. So why is it happening like that? So I started off with, well, are there auroras at solar minimum? Well, the answer is yes. I just gave you the answer that there are auroras at solar minimum. We don't often see them here in Fairbanks, but they're elsewhere. So farther north than Fairbanks. On average, the auroral oval is contracted at solar minimum compared to solar maximum. Now, I'm going to actually try to explain that to you. Why is the auroral oval somewhat smaller during, on average, at solar minimum compared to solar maximum? That's something we'll get onto in a minute. So what the cause is? What happens to the sun causing this change in the solar cycle? I'll be able to get to a little bit of that, but we really don't know this whole story. And the other thing, what caused the solar minimum to be so long? We don't know the answer to that story either. Now, you know, some of you might have heard of the Maunder minimum. The Maunder minimum happened in the 17th century, and it was a very, very long. It went through several cycles that there were no sunspots at all, and there were no auroras at all. That's something we know the sun did, but we have no idea really why it did it. But so I'm going to answer some of these questions, but not all of them. Here's a picture of the sun. This is sun taken in white light emission. So what that shows us is what we call the photosphere of the sun. This is the part that provides most of the luminosity, particularly in the wavelengths that you can see. Here's a sunspot. You can see one. Now, if you've got really, really good sight, I have to put my glasses up on off my end of my nose to see this. There are 3 more down there. They're not very bright, and from the back you probably can't see them. That's all the sunspots there are, but I want you to notice the positions of them. These sunspots are black on this picture, not because they're actually black on the sun. They're just not as bright as the rest of it. You know, this photosphere is at 6,000 degrees absolute temperature. And the inside of these sunspots is about 1,000 degrees less. So it's still very hot. It just doesn't look as bright. But it is a center of activity on the sun. In fact, the magnetic field of the sun is compressed in these sunspots. Now, if you look and compare these two images, first of all, you'll notice this is still the sun, by the way. It looks a little sick in this picture. But this is still the sun. This is a picture of the sun taken in X-rays. These are X-rays in the long wave region of the X-ray spectrum. But you notice that this is where that sunspot was. Now we've got a bright activity going on here where that sunspot was in X-rays. And down here where I told you there were some other sunspots, we've got another bright region. So what we see is that where there are sunspots, there is something else going on. And because this is bright, it means that it's actually very hot. So the environment around this sunspot is really very hot, and around that sunspot group also. But there's something else we should notice. Some of this sun looks black. Wherever you see dark in this picture, the electrons and protons that come out of the sun are coming off at high velocity compared to wherever it is bright. And so you can see there's something here which is called a coronal hole, which is a large dark area. And there are some minor coronal holes around here, which means that, and we'll get onto this again later, but it means that there are going to be some very fast streams of solar particles coming out of here, which will be going much faster than their companion particles in the main solar wind. And so that's going to lead to turbulence. We can see all that just by looking at this image. This actually, as you can see here, is 18th of January, so it was yesterday's image. Now here's a picture of the sun taken with a coronagraph. And the way this instrument works, it works from a satellite in this case. This black circle, it obscures the sun so that the bright sun is not visible to you. But what you can see are the pieces of the solar corona image where it's also bright. And so these are ejecta from the sun going out in different directions. This would be the ecliptic plane, with the ejecta going out towards the Earth at some times. But what you see on here is an event taking place which is called a coronal mass ejection. It's an instability that throws out a lot of coronal mass at one time. When those events occur, we get particularly strong aurora. And that doesn't matter whether it's a solar minimum or solar maximum. So I just said, well, we've got small sunspot numbers, but sunspots are the center of these coronal mass ejections. And the coronal mass ejection sends particles out that can eventually get to the sun, to the Earth rather, from the sun. Here's a picture of what happens there. This is now the edge of the sun here. This picture is in X-rays again. And what you're seeing is a loop. This loop actually is the shape of the solar magnetic field at this point. What you're seeing up around the loop is the light being emitted by solar particles which eventually will be in the solar wind. So this is the result. This is what we like to see, right? Rather nice aurora. This aurora is taken by a person called Ulla Christian Salomonsson. And if you can remember that name and you enter it into your Google search, you'll find he has lots of pictures like this. And I put one on this to show you because I think they're so good. I want to point out some things about the aurora that you can see. But if you've got a bright aurora like this, you've got something energetic coming from the sun. The lower edge of this aurora that I'm following with my pointer is probably somewhere around 60 miles in altitude. It might not look obvious to you, but if you follow these streaks upwards to up here, you're going to get to the upper edge of the aurora. That upper edge is probably more like 150 miles. So these are very, very long curtains of light, going from a lower edge of about 60, maybe up to about 150 miles. And it's a very long thing that goes from the horizon all the way towards the camera that's taking the picture. That might be as long as 500 miles. And then you see here some different colors. I pointed out the green that comes from oxygen earlier on, but you can also see some purple here. That purple comes from nitrogen, and it's not just any nitrogen, it's actually ionized nitrogen. That means it's a molecular nitrogen that has lost an electron. It's been ionized in the process of creating the aurora. And you can't see much else, but you'll see some other colors in some other pictures that I've got here. This is a picture by Jan Curtis, who used to work in our climate research laboratory at the Geophysical Institute. And this shows something that we call magnetic zenith. You notice that all these streaks are aimed away from a certain point. It seems to be a vanishing point, as you would get in a perspective diagram. Well, this is called the magnetic zenith. And the tops of auroral arcs in this diagram are right around that magnetic zenith. That's the height of about 150 miles, I said before. And the bottom of these ray-like things are around the 60 miles that I talked before. But now you'll see another color, and that's the diffuse red that is in this picture here. That diffuse red also comes from oxygen, but it comes at a lower energy level. That means it doesn't take so much energy to create this red as it does to create the green. And here's another picture. You'll notice that actually these pictures are a pair. If I switch back between them, you can see they look similar. This one was taken 30 seconds away from the first one, and it's the same kind of thing with the magnetic zenith here. These are looking a little yellow, but they're really green in actuality, and the red in the background. So here's some pictures of what you might see when there's a good aurora going, and that happens when you see those CMEs that I gave you a picture of. Now I've shifted the point of observation up into space, and this is the sort of thing that you might see if you had a camera on a satellite traveling above the aurora. So it would probably be at about 300 or 400 kilometers, or say 200 miles. looking down, and what you're seeing is, again, these very extensive arc-like structures that stretch out across the surface of the Earth. Okay, so this is some pictures of the aurora. Let's go on to say, what's the difference between solar maximum and solar minimum? Well, here it is. These are pictures of the aurora taken from a very high-flying satellite over Antarctica. And what you can see is the size of the auroral oval during a solar maximum event compared to what you can barely see here, which is a very small auroral oval on a solar minimum event. So what's happened, and the most obvious thing apart from brightness, is the actual diameter of the auroral oval. So then we take this information and we put it into some data, and we compare the number of these CME events that I talked to you about, which are here around 3 per day, as you see, at the maximum, compared to sunspot number that goes up to around 160. And so we've got a roughly straight line relationship, and in that relationship we can see that if we get down to the minimum, we can see that if we are at a sunspot number like we have today of somewhere around 0 in this region here, we're not going to get more than about 0.2 CMEs per day. That means we're not going to see much of the type of aurora I just showed you, because there's going to be one every 5 days maybe. But that would be an average. On the other hand, if we got somewhere near solar maximum, we might be having 2 to 3 CMEs per day, which would mean there would be a lot more auroras for us to see. Now I want to try to persuade you that there's a reason for this difference in the diameter of the auroral oval. And I'm going to start with a very simple picture which I think many of you may have seen. This looks like the Earth, but in fact what it is a uniformly magnetized iron sphere. And it's placed in a hole in a piece of paper, and what these are iron filings. And if you tap the paper that's got the iron filings, what you get are these shapes which represent magnetic field lines. So you could see magnetic field lines coming out and then across at the pole of the Earth down here, and you can see them going from the southern hemisphere to the northern hemisphere, with the equator being somewhat the axis over which that is symmetrical. So this is what happens with the Earth, and in fact it also happens with the Sun. The Sun has a magnetic field. And so what we're going to talk about is the interaction of the Sun's magnetic field and the Earth's magnetic field, and how that can give us the result that we see, that the auroral oval is smaller during sunspot minimum. So now if we just look and see what actually happens, we don't have a magnet that is lined up along the rotation axis. Actually the magnet is at some angle here, and so we have where that magnet axis comes through the Earth. We call this the geomagnetic North Pole here, and the geomagnetic South Pole down there, and we have auroras that are symmetric about those geomagnetic poles. Here we have the Earth, and here we have the field lines that close back on the Earth, the ones that go around like this, and then we have those that don't close back on the Earth. They go out somewhere into space. And those are the ones just in this junction between those that close back on the Earth and the ones that go back out into space. That's where we find the aurora. That's the location of the aurora oval. And the next slide shows that more clearly, that now we have those closed field lines, the ones that close back on the Earth, colored sort of orange, and the yellow ones which go out into space, they're called the open field lines, and it's at that juncture where we find the aurora. So what's happening then, you can see that if the aurora oval diameter changes, it's because we are getting more field lines that are open, and they're making a bigger area in the polar cap here in order to push the aurora further out. So now we look at some pictures here. These are taken from satellites and showing you an auroral oval. This is not during solar minimum, but it illustrates the point that all this space in here has got magnetic field lines going through it that go out into space, and the space around here on the outside, they close back on the Earth, just like I showed you. And the same thing happening here. This is an aurora over the South Pole, but now the same thing. These inside here, the magnetic field lines are going out into space, and the ones on the outside of this are closing back over the equator. Happens both poles the same. What is happening to bring magnetic field lines into this area here is that there is a merging of magnetic field lines from the sun that tend to fill this space. And what is happening to reduce the size of the auroral oval is a merging that is taking these field lines and allowing them to, releasing them to go out the back of the tail. And so then we have at any given time an equilibrium that exists between those that are being supplied by merging from the sun and those that are being lost by merging out into space behind in the anti-solar direction. So the size of their oval depends on the relative speeds of those two processes. So here I have another movie, and this one now shows you with a map underneath some aurora that occurred in the year 2000, again taken from a satellite. And you see that this starts off with a auroral oval that's pretty big, and then it gets smaller, and it will end up pretty small indeed. And so what has happened in this is that we've had magnetic field lines come from the sun, make the aurora pretty big like it is there, and gradually those field lines are being lost out on the tail side of the Earth, and so the size of the oval is getting smaller. So I want to show you this now diagrammatically. Here is the smallest auroral oval we're likely to see. It's got the label 0 underneath it, and you can see that if you look at it over this is now drawn, of course, in the northern hemisphere. This is the Alaskan coast here, and it skirts inside Siberia, and it goes north of Norway, and it goes just clipping the south end of Greenland across Hudson Bay and back. And that's the minimum size of auroral oval that we might expect. It gets a little bit more excited, and you see the auroral oval gets fatter and a bigger diameter. And as you go to a higher excitation here at 2, it's getting bigger and bigger again. And then you begin to see it really getting quite large, and we're beginning to see the auroral oval getting down into the lower 48, which is what we have here at a level 8 and a level 9. We could expect to see the aurora down in the northern states of the United States, with the southern edge at 9 here down into Texas. Now, you probably all heard that the aurora sometimes gets to Texas. Texans are quite proud of telling us that they have auroras too. But for the most part, they don't have them. And that's because we don't have this level 9 very much. But then you've got to think about what I just said about solar magnetic field lines. In order to get a condition like this, you have to put an awful lot of those solar magnetic field lines into the polar region to make that expansion happen. And that takes an awful lot of excitation on the sun to do that. And so this doesn't often happen. Now we get down back to this area here. This minimum size happens because there isn't much excitation on the sun. Because the excitation of the sun is so low, we are not filling that region with field lines, and so we are not making the diameter larger. So that's the reason why this situation exists, where we have a typically small auroral oval at solar minimum. Now I want to show you what is happening in the space between the sun and the Earth as to how we are getting solar shock waves coming from these CMEs. This is actually a very big event that I've shown you here. It happened back on Halloween in 2001, but you can see how here's a shock wave coming out through the solar wind. It is overtaking everything that is in its area, pushing it in front of it and creating a big shock which passes over the Earth. Now that's a big shock wave. And what I'm going to show you next is actually what's happening today, or actually It's the 17th, 2 days ago. 1 day ago, I'm sorry. Here is the same kind of map. The sun is here in the center. Here's the Earth and Mercury, Mars, and Venus. And these red lines here are those field lines that are going away from the sun, and the blue ones are going towards the sun. So we have regions of field lines going towards and regions of field lines going away. But now what we see is that in the vicinity of the Earth, we have this region here where it appears that the field lines are closer together. Now you remember I talked about a coronal hole earlier on, the black area on the sun that has the high-speed stream. This is a high-speed stream coming out into the region of the Earth and the Mars and so on. And you'll see that if we look at this as a sequence, and I've got it drawn here, going a step at a time here, half a day. So here's 17th, where the stream is, and then the 12 hours into the 17th, and so on. And Earth is up here. You'll see as time goes on, this stream is getting closer and closer to Earth. And in this simulation that we've got here, on the 20th, it's getting very close. When that stream, a high-speed stream, reaches the Earth, there will be enough excitation to bring some auroras. So if anybody's going to be looking for auroras in the next period of time, the 22nd and 23rd is when we expect there to be a high stream passing us. Now that high-speed stream, because of the turbulence associated with it, is expected to create some auroras. So there's a forecast for you. We think that will happen. Now I want to show you something which is the spread of information that we have. These are, now going back to sunspots, these are sunspot results that have been obtained since about 1625. And this black line shows an average drawn through this. And so we can see that the average number of sunspot cycles averaged over a cycle is by no means constant. In fact, at the present time, it's higher. Well, it's not higher right now, but it has been in living memory higher than at any time since this business of looking for sunspots began. And I mentioned to you in the 17th century, there's this Maunder minimum here, long period of time where you didn't see any of this 11-year cycle in solar sunspots. But you could also see that there's also periods when you get a large number of sunspots, like there's one here with 200 on the sunspot scale, and there was another one here, 1957, where there was a similar number, 200. And yet, when we had this one here at about 1970, that one was a lot less, and we looked like we're going to have another one that was a lot less coming up at the next maximum. But if you look at minima now, you see not very many of these minima actually reach the zero that we saw in the diagram I gave you to start with. These minima end up at around 10 and not 0. So we've had a very deep minimum. But if you look here, in 1950 there was a fairly deep minimum, but much more so in 1900, and then again much more so around 1800, and then around 1700. So there's this kind of 100-year variation in the depth of the minimum of sunspot activity. And this would actually, of course, remain that the auroras that you would see at the same time would be as small in the diameter as the ones that I showed you. And so here's for comparison, this is where we are. We're just coming out of that very deep minimum there that I was referring to. We could get more information about auroras that happened over longer periods of time before the present. This is a number of years before present, going to the right. So we're at 1100 years before the present back here. And this is the present right here. And then we have what's called here the carbon-14 record. Now, it so happens that the carbon-14 record is related to the sunspot activity. And what we have found is that there's a modern maximum, and I was talking about that, and then there's the modern minimum, and we went back to the modern minimum in the sunspot mechanism that we talked about. But if you go now and look at carbon-14 records, you find there's another minimum around 500 years ago, and then around 700 years ago there's another minimum called the Wolf minimum, and then there's a medieval maximum, and then the Oort minimum, and so on. And if you look and see how active the sun was back here in the medieval maximum, it's about the same as what it is today. But the sun has been a lot less active in the meantime. So this business of having solar minimum auroras can be traced using the carbon-14 mechanism, and it shows that indeed things have been pretty variable over that period of time. But here we are back at that auroral record I showed you, where this is a solar minimum case over Antarctica, and if you want to fit it and show exactly what it looks like, then I'll take our level 0 aurora and put it over the top. Now you can see actually it's a little bit inside the level 0 aurora as I fitted it. In other words, that the aurora that existed at the time of this picture was really very, very inactive. And then I could show it to you again just to convince you by putting it in pixel-wise and taking away that this is a pretty good fit. But it is very, very inactive. So now we are at so auroras at minimum is the condition that we have. This is again something from Toolik Lake, and this is typical of seeing in the lower part of the picture that the auroras are north of Toolik Lake quite often, and so this is the kind of condition that we have right now. So just to recall, aurora at solar minimum still exist. They exist north of us. They are there because the aurora oval has contracted. The contraction of the auroral oval has happened because we get fewer solar magnetic field lines included in the magnetic field of the Earth at the time of solar minimum. And this is going to continue for several years yet. On the other hand, it's going to get better. So with that optimistic note, I'd like to thank you for listening, and I'll answer some questions. Yes, at the back.
So, why is it better, like at midnight versus 2 or 3 or, oh, hello. So, the time of night that you can view it best?
Yes. Well, the reason for that is that there are some asymmetries in the pattern that I didn't show you for simplicity. What happens is that the aurora is closer to the equator in the midnight hours than it is at any other time. And so because it's closer to the equator, if we normally see the aurora to the north, then it's going to come down towards us as midnight comes. So that's one of the reasons why we can see it. The other one is that where we are here, we can't see the aurora in the daytime simply because most of the time it's too bright. But you can go to places where it is possible to see the aurora in daytime, but you have to go where it's dark in the middle of the day. As Dan White said, I've been to a number of... Something's happened somewhere. I didn't ask for any sound, did I? Oh. I've been to, it was a CME, yeah. I've been to Spitsbergen, which is 78 degrees north, 15 degrees east off the northern coast of Norway, where in the middle of winter it's dark all the time. And then you can see the daytime aurora overhead, and the daytime aurora will be further north than anything you see at the nighttime because of that distortion that I talked about. Yes? Okay, thanks. Thanks, Dan.
There's a number of microphones.
This one work? Yeah.
Yeah.
Okay. So these spectacular pictures of these auroras, you know, where is the best place to see the best? And there's like aurora touring companies. Like, to me, it seems like Siberia or possibly Canada would be the best places on Earth to see the really good ones. And are there aurora touring companies where you can go and see the best?
There certainly are companies that make a living out of taking people for an auroral experience. The people, if you look at a plot of where do you find in Alaska, for example, the most frequent auroras, now averaging over all time, you'll find it's a place like Fort Yukon. Now, if you do the same in Canada, it will be a place like Yellowknife. And that's where you'll see the most frequent auroras. Now, that doesn't mean to say necessarily they're the most spectacular. Actually, you're going to see more spectacular auroras a little bit further south, because when you get I'm showing you the auroral oval expanding, that's because there's a lot of activity coming from the sun that merges a lot of magnetic field lines into the polar cap. That creates more active aurora. And so if you want to see really active aurora, then you might want to go further south than Fairbanks even, but they'll be relatively infrequent. And so there's that difficulty about it. Yeah?
Siberia.
Siberia will be the same. I mean, there's really not much. The aurora is no favor of a particular national location. It's a matter of your magnetic latitude. And magnetic latitudes in the northern part of Siberia will be similar to the experience you would have at the same magnetic latitude in Alaska. Yes.
Thank you. Two questions. First, where was the carbon-14 data taken from? Was that atmospheric samples out of ice cores, or?
Yeah.
And the second question, well, I'll let you answer that one first.
Okay. So I knew somebody would ask me about the carbon-14. Actually, there's a man at the back there who told me I shouldn't use that. He's one of my co-authors. The carbon-14 data is perfectly good. To understand why it actually works this way is you have to realize that carbon-14 is created by cosmic rays. And cosmic rays are coming from the galaxy, and they're not coming from the sun. Most of them are not. They're coming from the galaxy. And their path to the Earth is impeded by what I was telling about, the solar wind. So the more dense the solar wind, the fewer cosmic rays will reach us. So if you can find out by looking in the record how much carbon-14 you have at different times by looking at dating, of course, then you'll find out if it's got a minimum in an occurrence, it will be because there's a maximum of the solar wind, because the solar wind has either absorbed it or scattered it so it doesn't get to the Earth. So that's why this record works. And I don't know, did you want to know something else on that?
Well, I was curious where the data was actually, where were the measurements taken?
I don't know that, actually, but I could get that answer for you because it's in the paper I got that data from.
The second question was, you may have alluded to it already. You said the infrared variation in the sun is very minor,
yes,
compared to the ultraviolet. Just I guess a generic question, just how stable is the sun as an energy source?
Well, now it depends on your time scale. On this time scale of the life of a star, not very stable, because eventually our star will die. But on our lifetime scale, it's very stable. That is, if you take the sum of wavelengths going from the infrared up until the near ultraviolet. When you get into the far ultraviolet, you can get several orders of magnitude difference between one circumstance and another. But the fortunate good thing for that is that this kind of ultraviolet radiation doesn't penetrate to the surface. It excites the atmosphere at a high altitude. And a good example of that is the temperature of the atmosphere at, say, at an altitude of around 200 miles. That temperature today is about 700 degrees absolute. Don't worry about the absolute, just remember the 700. I can't convert these to Fahrenheit in my head. Then if you get to the peak of the solar cycle, that temperature might be as much as 1800. So it's gone up more than twice, just because we've got more ultraviolet radiation coming in, which in the end is heating this upper atmosphere. But you don't see that effect down where we are, because all that ultraviolet has been absorbed. well before we get down even into the stratosphere. So actually the big differences are in the ultraviolet. The small differences are in the infrared and the visible. Any other questions? Can't see the hand up. Oh, yes, okay.
So you said that there will be like auroras north, but do you know when there will be a forecast for Fairbanks?
Oh, well, there is a forecast for Fairbanks every day, but the problem with it is that you really can't see much from Fairbanks. And what you want to know is, when will you next be able to see something from Fairbanks? Is that right?
Yeah.
So what I was telling you a little bit ago is that we're expecting a fast stream from the sun. That will come from that dark area I showed you on the orange image of the sun that I had. Mm-hmm. And that fast stream will be bringing turbulence that will probably create an aurora. So on the 21st or the 22nd, I expect there will be some aurora to be looked at because of that fast stream that's going to arrive here. Yeah, but you need to go somewhere good and dark, and actually you have to ask your mother if you can stay up late. Because, it won't happen at 8 o'clock in the evening. The good thing about the 21st and the 22nd is that it's getting towards the weekend. Anybody else? Any other questions? Back here?
All right, you said that the most particles were coming from the area of the sunspots, correct?
Yes, in that vicinity, and actually it's further out than the sunspots, yeah.
All right, what's causing the sunspots to release more particles? Is that the magnetics of the sun?
The sunspots themselves are a phenomenon that just locates an area of activity on the sun. The energy that is creating these coronal mass ejections is coming from a reorganization of the magnetic field. Now, I'm trying to think of something that would give you a feeling for this. If you have a very powerful magnet, and you actually were able to measure how many magnetic field lines there are in a given area on that magnet, it will be high if the magnetic strength was strong. What you've got in the vicinity of a sunspot is a very strong magnetic field. And if you can convert that magnetic field into other forms of energy, then you'll create heat generally. And that's what's happening. The areas where there's very strong magnetic field, some of that energy is being converted into another form. That form, in the end, heats the particles that are in the area of the sun. It's really the sun's atmosphere. And so they generate that big arch that you saw in that picture, and that is releasing energy into the solar environment, and some of that comes to us. So it's really an energy conversion thing. It's being stored in the magnetic field, and it gets released.
So otherwise, other than the sunspots, it's fairly uniform in its distribution of the particles?
Well, as I said, where you saw black, then the particles are actually much higher velocity. They're called high velocity. That's those places where you've got a coronal hole, you'll get high-speed particles, and where the places where there's no coronal hole, you'll have about half of that speed. You just reminded me that I've got another video that I could show you that I stored up, which is showing you one of these solar prominences that you were just referring to. If I can get this to load. And you can look at that. You can see a prominence working there. And you'll see it will loop back several times. This is what's happening around an area which has at the center of it one of these sunspots. And you can see how much energy is being released. Another question? Yes?
In terms of the auroras
on the ground, do they make any noise?
Do they make any noise? Okay. Let me. Some people hear them. That's the first thing. There's enough people here, I would say, for at least 5 or 6 of you to say you have heard the aurora. Anybody heard the aurora? 1, 2, 3, 4, 5. Yeah. Okay. That's what I thought. About 2%. This is really something that is true and is real, that people hear the aurora. The question is, what is causing what they're hearing? Now, if I were to ask these people and put them in an interrogation room and find out, did they hear the aurora immediately they saw the light, or did it come 5 minutes later? Immediately you saw the light? How much later? Minutes? Well, okay. Minutes later could have been real sound, because it takes 5 minutes actually for the sound to come from the aurora down to the ground. But most people will answer that they see the aurora and hear the sound at the same time. Not you. I know you're scientists. That's the trouble. But so here's the problem. If the sound and the light is seen at the same time, because they don't travel anywhere near the same speed, this cannot be because sound came from the phenomenon that created the light, unless the sound is only the local effect of something else. Now, it could be that, because radio waves travel at the speed of light. Radio waves are created by the phenomena that create aurora. Now, if that radio wave came and did something in your environment that made a sound you heard, then that could be a reason for it. Now, if it were ordinary sound, then we will be able to hear it with a microphone. There's been a lot of money spent and a lot of patience exhausted trying to record the aurora. And I only know of one paper in the peer-reviewed literature that says any aurora was ever recorded. But I know of a lot of times people trying to do this. And so I think that the sound, in the most part, that people hear is not sound in the environment, but sound perceived by the mind, which may not be actually sound itself. Sorry? Yeah, I understand. And sometimes it's your husband's voice, and sometimes it isn't. Yeah, I know. But let me just put it one step further. Some people are very sensitive to what is called power line radiation. That is the radiation that comes from power lines at 60 hertz. Their being senses that, and they get sick, some of them. So we know that radio waves have the power to affect a person's ability to do things, maybe even to hear something because of it. And so I wouldn't put it past the possibility that some people are receiving something that is really a radio wave and converting it into an experience they think it's sound. What we do know is that for the most part, what people report would not support the idea that this real sound. Now, even having said that, you didn't expect to get an answer this long, I know. Even having said that, there is a form of sound that is known to be receivable and does happen, and that's called infrasound. Infrasound at frequencies of 10 hertz down to maybe 0.1 hertz is recordable and does happen. And that's a course of investigation. And Hans Nielsen, who I had in my list of co-authors, who's at the back of the bill, this assembly here, could tell you about that, because he's got some money from the National Science Foundation to do it. Yes.
We saw photos of the northern lights from Earth and then from space looking down.
Yes.
Are there any photos taken right in the middle of them?
In the middle of the northern lights?
Yeah.
You mean like in the middle of the circle, looking outwards?
Well,
or how do you mean? You mean actually taken because you're actually physical in the middle of it?
Well, maybe not a human, but yeah. Like a satellite
I
orbiting
think-
at the
I
same
think
level?
the answer to that is that people have taken data about the aurora by flying through it. I see, we've flown rockets from Poker Flat that have gone through the aurora, haven't we, Neil? So the answer is we've flown through the aurora and got data. However, I wouldn't expect it to be a very exciting picture, because it would be like taking a picture of a cloud from the middle of a cloud. You don't see very much because you're in the middle of the structure. But if you were to say, well, what else is going on that you might sense? Well, you get pelted by high energy particles if you're in the middle of it. That would happen. Yeah? Someone's coming.
Good. And, understanding the relationship between the auroral activity and the solar maxima and minima, has there been any correlation with that, say, in atmospheric heating or maybe climate patterns over a long period of time?
Believe me, people have tried very hard. If you realize there's more money in climate than there is in auroral science, then you'll try to connect the two. The answer is there are very weak connections between what you can see in the solar cycle and what happens in climate records. And they're not really fully understood. They exist more statistically than they do in the minds of people as a mechanism. Certainly, I said there's a fraction of a % change in the radiation. Well, if there were not very many other changes, that fraction of a % would be important. The trouble is that there are other changes that go on, and it's masked by the bigger changes that occur. And so it's not absolutely certain that it's important that there is a solar cycle in the climate. There's a theory about the fact that rain is caused by nucleation centers making the raindrops in the first place. And those nucleation centers can be caused by cosmic rays. I mentioned cosmic rays earlier. So if there are more cosmic rays coming down, then we might get a bigger rain pattern, and that might affect the Earth climate. And that could be a reality. But we don't know enough about it yet to be able to say how well it works in coordination with what we record about the climate. There's a few examples. Yes? No? But actually I think they all want to hear what your question is.
I was just wondering if there were aurora borealis on all the other planets in our solar system.
A good question. That's a good question because I know the answer. Every planet that has an atmosphere and has a magnetic field has auroras that look like our auroras to some extent. And so let's go out from the center of the sun, right? We look at Mercury. Mercury has a magnetic field, but it has so little so little atmosphere that you don't really see very much. And then you get out to Venus. Venus has a pretty thick atmosphere but no magnetic field. And Earth has an atmosphere and a magnetic field, and we get auroras. Mars has a pretty spotty magnetic field, but it has an atmosphere, and you can see some auroras in Mars, but they're not very dramatic. And then you get out into the giants. So then you get to Jupiter. There definitely are exciting auroras in Jupiter. But believe it or not, they're not exactly like ours, not only because the gases aren't the same, but also because the auroras of Jupiter are created by internal processes more than the external involvement with the solar wind. That's because Jupiter is a huge planet, and its magnetic field is so strong that it excludes the solar wind to such an extent that most of the processes are related to the moons of Jupiter that you're seeing. And the same kind of story exists when you get out to Saturn. Now, then the auroral record is getting thinner and thinner because a lot of this was done using the Hubble telescope, And if you go on the web, you can get pictures of the auroras from these different planets. But basically, it is this: if you've got a magnetic field and you've got an atmosphere, you're going to see nice auroras from time to time. Yeah.
I was just wondering, what is the time span of this CME that we've been watching?
This is, I think something of the order of an hour or so, not very long. So it might erupt more than, the same excited area might erupt more than once, of course. We're just seeing one cycle of it. I've forgotten that you were looking at the sun there. Yes.
I was just wondering if there was some applications, products that you know about that have come from auroral studies, or some engineering, some anything that has entered the marketplace that was directly involved from
from looking
things
at the
that you've
aurora?
learned or people have learned from the aurora.
Well, I guess there are, because we push the science of doing observations at very low light levels, just like astronomers do, then some camera systems have been developed that are very high performance, let's say, and we keep pushing that particular area. Again, I keep mentioning Hans Nielsen here, because wishing I didn't, but he has access to a very fast camera that will take pictures at 10,000 frames per second. Not only useful in the aurora, but that kind of technology is developed because of the need for it to do auroral science as well as other kinds of science. I should say that if you, I don't really want to keep you here if you're tired of the questions. I'm not tired of answering them, but you might be tired of listening to them. Yeah.
Does the gravity have any effect on the auroras?
Well, gravity is pretty important, isn't it? I wouldn't be standing up like this if I didn't have gravity. But the answer to that is that the distribution of the atmosphere around the planet is there because of gravity. But that's what holds the air in on the planet, because we have gravity. Otherwise, it would all float away. So we wouldn't have an atmosphere if it weren't for gravity. So that's one thing. And then when you think about what happens on the sun, everything that happens on the sun also is affected by gravity, although it doesn't actually stimulate any of the things that cause the emissions from the sun. Just that the sun wouldn't exist without gravity in the form that we see it. So I'd say that gravity is important environmentally, but it isn't key in creating the particular displays that we see. But it's a good question. We actually need gravity. Yes?
Why isn't the aurora the same color? Like, why are different colors?
Well, the aurora is created because there are particles coming into the atmosphere. Mostly it's electrons that cause this. The electrons hit whatever they find. And so you know already, don't you, that there's nitrogen and oxygen in the atmosphere at this level. Well, if you go higher in the atmosphere, you find not only molecular nitrogen, but you find atomic nitrogen, and not only molecular nitrogen, but also ionized nitrogen. So you can get different forms of the same gas. Every different form gives you a different color. And even in the same item, like I told you about oxygen producing red and green, you can get those two colors out of one atom. So this is all coming because of the composition of the atmosphere. It has oxygen, it has nitrogen, and it can be ionized, and it may not be, and it might be molecular. Each one of these create a different color.
I just wondered, that's a fascinating...
One up here.
It's a fascinating picture there, and I just wondered if you could kind of tell us a little bit about how much energy is taking place here at this event? What kind of mass we're looking at? What kind of, what's the surface gravity on the sun?
Well, I'm not sure whether I can answer the gravity one. How much energy? It's huge. I could tell you that, I could give you an idea of scale, because I haven't measured that. But if you take how much power is deposited in the Earth because of a big one of those, that would be something of the order of 500 gigawatts power liberated at Earth. Now, we're only actually getting access to a very, very small quantity of that total energy that's coming out of there. So it's going to be a very large number times 500 gigawatts, which is the power generated on the sun. So if I was to give an estimate of that, I'd say it has to be more than 1,000 times that. Probably that's an underestimate.
Why don't we do one last question here in the back?
What kind of noise does it make, the aurora?
Oh, well, I've never heard the aurora, but the people that have, a rustling sound? A buzzing sound. Yeah. But it doesn't, like static. It doesn't sing a tune. Okay, all right. It's a buzzy sound or a rustling sound, most people say.
Well, you all join me in applauding Roger, and thank you for speaking tonight.
Sure.